we discussed exact equations, if we had an exact differential, m is d phi dx, n is d phi dy for the same function phi, dy equals 0, then this whole equation was just d phi equals 0. You could integrate it to get phi equals a constant and get implicit solutions to the differential equation. But what if you're not so lucky? What if there isn't such a function phi such that this is it's partial with respect to x and this is partial with respect to y? We can try and make it so in the following manner. We can multiply through by a function mu of x and y. I didn't put the x and y on here, but if you can multiply through the equation by mu, a function of x and y in general, such that mu times m is the derivative of phi, and mu times n is the derivative of phi with respect to y, this is exact, then we call mu an integrating factor. So we can hope for that. That's a little less difficult. Well, what happens is, actually, this is not so easy as it sounds. It's very hard to find an integrating factor for a general differential equation. There's really only two common cases where it works kind of frequently, and you see it in a lot of textbooks. So I'm going to omit all the other cases, and the two cases that occur most frequently are where mu is only a function of x or mu is only a function of y. Sometimes that's a good strategy. If mu is only a function of x, what do we need to do to make this exact? Well, remember the criterion for deciding if an equation is exact on a simply connected open region was that the partial derivative of this with respect to y had to be equal to partial derivative of this with respect to x. So if we want our multiplied equation to be exact, we need partial of mu m with respect to y to be equal to partial of mu n with respect to x. Then this new equation will be exact. So here's the criterion right here. We want to find a function in general of x and y, but for our purposes, we'll just assume it's a function of x only or a function of y only. Those are the two important techniques. Has to satisfy this equation. Well, then the strategy is to do this. Find the integrating factor, multiply through by it, then solve the equation by your method for exact equations. That's all there is to it. And then, here's the derivation. I'll do the derivation and then go back to the formula above it. Suppose mu is supposed to be a function of x only. Then this is the equation we had to satisfy. Mu m partial with respect to y equals mu n partial with respect to x. When you work this out, if mu is a function of x only, then mu m partial with respect to y is just mu times partial of m with respect to y, because mu is treated as a constant. But over here, not so, right? Now you're taking partial with respect to x, since you need a product rule. Mu x times n plus mu times nx by the product rule. Now you can rewrite this in the form, a little algebra, as mu x plus mu times nx minus ny over n equals 0. Just a little algebra from this one to this one. And then recognize, wait a minute, treating y as a constant, this is actually a linear equation in mu as a function of x. Right? This is d mu dx plus mu times a function of x only equals 0. Provided this is only a function of x, this is a linear equation for mu as a function of x. There's a formula for that, right? The formula says you let you choose an integrating factor for the linear equation, mu also is the letter, equals e to the integral of whatever multiplies the dependent variable, dx. So mu equals e to this integral dx is the integrating factor, and if you write out the formula, 1 over mu, integral of e to the mu times the right-hand side 0 dx, what you get is just a constant times e to minus this integral as the solution. In other words, you don't have to memorize the proof here, but when you use the method for linear equations, you get this, that the solution for mu is that mu equals e to the integral m1 minus nx over n. Similarly, if you want to find a function of y only that's an integrating factor, you have to satisfy the same criterion. Mu my equals mu n, this should be a little x here, sorry for the z, x. The same criterion I wrote up here. But now mu is a function of y only, so the left side is a product rule. Mu ym plus mu my, and this one, equals the derivative of the right side. Mu is treated as a constant when you differentiate with respect to x, because it depends only on y, and you get mu times nx. So product rule on the left and no product rule on the right, because mu is treated as a constant. You rearrange this algebraically, get mu y times mu y plus mu times my minus nx over m equals 0, and find that if my minus nx over m is a function of y only, then this is an ordinary differential equation for mu as a function of y that's linear. And so you can solve it by your linear technique. So you write the formula for that and solve it, and I'll just say what you come up with now. Is this result, that mu, a function of y only, is e to the integral of nx minus my over m dy. So we have these two integrating factor cases that I've labeled 220 and 221. They come out of my notes. They're in chapter 2 there. The top one's not showing up. There we go. If an integrating factor exists that's a function of x only, then this will be it. So this is what you do. You look at the original differential equation. If my minus nx over n is a function of x only, then there exists an integrating factor that's a function of x only, and this is it. E to the integral are the same. On the alternative, if this doesn't work, suppose nx minus my over m instead of n is a function of y only, then e to the integral of that is an integrating factor. That's what we just proved. So this still isn't applicable in a whole lot of cases, but in enough cases that it's the main way we can make a non-exact equation exact is these two cases. So here's an example of using that to solve a differential equation. Suppose I'm given that dy dx equals 3x minus 3xy plus y squared over x squared plus xy. That looks difficult. All our previous methods fail, right? It's not linear, it's not homogeneous, you turn it upside down, it's not anything. We don't want to just get an approximate solution. If we can solve it, this can actually be solved by an integrating factor. I first multiply through by x squared plus xy and dx, and then I take everything over on one side. By algebra, I can put it in this form. So you multiply both sides by x squared plus xy dx. And then you subtract over and you get this. So this is the equation in differential form, if you will. M dx plus n dy equals 0. We'd like to just integrate it exactly, but alas, it doesn't work. How do you know it doesn't work? You use the test from last time. This is m, this is n. We take partial of this with respect to y, and let's see what we get. 3x plus 2y. And then we take partial of this with respect to x. 2x plus y. They're not equal, right? 3x plus 2y is not equal to 2x plus y. So my and nx are not exact. There is no function such that this is partial phi with respect to x and this is partial phi with respect to y. We can't apply the method for exact equations here. So we're going to hope that we can multiply through by some function of x alone or some function of y alone that will make this an exact equation. So what would we do? We try those two things we said. We'll compute my minus nx over n, meaning partial of n with respect to y minus partial of n with respect to x, all over n. We're going to hope that's a function of x only. Let's see. Partial of this with respect to x is 3y plus 0. I'm sorry, partial of this with respect to y is 3x plus 2y. And there it is. All right. And then we've already calculated them. partial of this one with respect to x is 2x plus y. And so we take my minus nx and divide it by n, x squared plus xy. And, oh boy, that's got both variables in there. But a little algebra shows the top is x plus y and the bottom is x times x plus y. Some of this canceling in here. And so the whole quotient is actually 1 over x. It is a function of x only. When my minus nx over n is a function of x only, e to the integral of that is an integrating factor. Well, e to the integral ln absolute value of x is absolute value of x because e and ln undo each other. Which means an integrating factor is to take mu equal x for x positive and minus x for x negative. That's the definition of absolute value, right? If x is negative, minus x is positive. So we'd like to use that. However, that's not necessary because we look at the original problem. dy dx is equal to, the bottom is x times x plus y. You can't, when x equals 0, the quotient isn't defined. So you're really only interested in solving this either on the interval x greater than 0 or on the interval x less than 0. So we can just say, suppose I solve it on x greater than 0, I can use x for an integrating factor. If I solve it on x less than 0, I can make minus x an integrating factor. But better than that, any multiple of an integrating factor is an integrating factor, if you think about it for a second. In fact, this is just, when we write this, I said ln of x, and I left off the plus c, right? I could have put on a plus c, and what you find out is e to the ln of x plus c is a constant times e to the ln of x, which shows already I could have put in a constant here if I wanted to multiply it. Suppose I make a constant, anyway, so I multiply any equation, any integrating factor by a constant is still an integrating factor. So I could just multiply this by minus x and say x, without the absolute value, is an integrating factor either on x positive or on x negative. It doesn't matter. Because any multiple, I can take minus 1 times this integrating factor, get x, it's still an integrating factor. All right, so I'll multiply through by x on this equation, and I get, you can see, 3x squared y plus xy squared dx plus x cubed plus x squared y dy equals 0. And now I check it just to make sure. It's actually, as long as I didn't make a mistake, it is exact. I can find phi, but you might check it. Partial of this with respect to y, just to make sure you didn't blunder here, right, is 3x squared plus 2xy. Partial of this with respect to y, with respect to x, is 3x squared plus 2xy. Aha, but it is exact. I did this correctly when by multiplying through by x. I made the equation exact. Now, this to apply your method for exact equations. You integrate this one with respect to x, right, partial integral. And let's see, this is x cubed y. Partial integral of this with respect to x is 1/2 x squared y squared. Then there's an arbitrary function of y because y is treated as a constant. This is the constant treating y as a constant. Partial integral of this one with respect to y, reminding you from last time, means you integrate this treating y as a constant, so the arbitrary constant you're added on for the integral can be any function of x, and treating x as a constant. Integral of x cubed with respect to y is x cubed y. Integral of x squared y with respect to y is x squared over 2y squared. And now here we have that phi has to equal this because of the partial integral here. Phi has to equal this because of the partial integral here. And they'll be, these two terms match, these two terms match. This time there's nothing left over, so f of x and g of y can only be something that doesn't depend on either x or y. An arbitrary integrating factor is x cubed y plus x squared y squared over 2 plus c, not depending on either x or y. For simplicity, let's choose c equals 0 because it doesn't matter. We want any phi whatsoever, such that d phi dx is m and d phi dy is n in the equation. So let's choose constant 0, and we have this for phi. And then the solution, recall, for an exact equation is just phi equals a constant. So these curves implicitly provide solutions. Well, you can actually solve this for y. If you think about it, it's a quadratic equation of y. You rewrite it as ay squared plus by plus c equals 0. So you write it in the usual form. And the quadratic formula then gives you minus x plus or minus root x to the fourth plus c over x is the solution. All right, here's another one. Solve this one by integrating factor. This one is put in this form, 2y plus 3x minus y squared quantity times dy dx equals 0. In order to apply the integrating factors method, or hope that it works, I have to first multiply through by dx. So I multiply dx and get it in the differential form, 2y dx plus 3x minus y squared dy equals 0. And now I check it. Maybe it's exact already. Maybe I'm lucky. Partial with this with respect to y is 2. Partial with this with respect to x is 3. Oh no, it's not exact. Well, I can hope to find an integrating factor. So I try my minus nx over n to see if it's a function of x only. If it is, then e to the integral of this will be an integrating factor. But I try that. Partial of n with respect to y is, we already did it over here, was 2. Minus partial of n with respect to x was 3. My minus nx is minus 1. All over n is 3x minus y squared. So this is my minus nx over n is not a function of x only. So the first integrating factor method won't work. Well, let's hope that nx minus my over m is a function of y only, because then I'm out of tricks, right? So nx was 3, my was 2, all divided by m was 2y, and sure enough I get 1 over 2y, a function of y only. E to the integral of this will be an integrating factor, so I take e to the integral of 1 over 2y dy, gives me e to the 1/2 ln of y, which remember you can bring the 1/2 in the exponent. This is e to the ln of y to the 1/2. E and ln undo each other, you get y to the 1/2 or square root y. So square root y is an integrating factor of this equation, a function of y only. Multiply this equation through by square root y. Right, we'll get 2y to the 3/2 plus 3x y to the 1/2 minus y to the 5/2 dy equals 0. And if I did everything right, this will be exact. You don't have to check it, but it's easy. You might just do it to make sure you didn't boo-boo here. So take, I forgot my dx on here, didn't I? I should do dx. Take partial of this with respect to y, and what do you get? You get 3y to the 1/2. And then you take partial of this with respect to x, you also get 3y to the 1/2. Check the equation is now exact. Even if I don't do that, I can just try doing this and see if it works. If it works, it was exact. So I'll integrate m with respect to x. So I'll integrate this with respect to x and get 2x y to the 3/2 plus the arbitrary constant that's a function of y only. I'll integrate this partial integral with respect to y and get, let's see, 3x y to the, and I'll get 2x y to the 3/2 minus 2/7 y to the 7/2 plus an arbitrary constant, arbitrary function of x for the integration constant. And now can I make these match? Of course I can. I already proved it's exact when I check my equals nx. So there's got to be a way to make these match up. These terms match. Then this one must be part of g of y. And the rest of g of y is a constant not depending on x or y. And f of x must just be a constant depending on x or y. And you get that an integrating factor is the function phi that has the right partial derivatives for this equation we made exact is 2xy to the 3/2 minus 7/2 y to the 7/2. You can put any plus c on here, right, and it's still going to work. There's always an infinite number of these because of the plus c. But you don't need it. Here's one of them. And so all solutions are any one of these equals a constant. And here are the solutions implicitly given to this equation. You can try and solve this for a while, also I think it's not worth the trouble. I'll just say, this is the method of integrating factors. When a differential equation is not exact, you can try multiplying through by a function mu of x and y to make it exact. If my minus nx over n is a function of x only, then e to the integral of that is a integrating factor, and you can change the equation to exact. If nx minus my over m is a function of y only, then you can take e to the integral of that and get an integrating factor. Either way, you get the equation exact and integrate by our method of the last section to solve it. It's just a 1-2 step. Find an integrating factor, integrate to find phi, and find phi, write phi equals a constant, and you're done. I'll just mention there are a few other integrating factors. You can Google this on the web, integrating factor. They're so seldom used, we'll just learn these two. Try these on these problems.